Alright, welcome back everyone. Here we are in section 2. This is applications of maxima and minima. This is probably one of my favorite sections. It's admittedly quite difficult, but a lot of reasons. I mean, this is essentially why humans still have jobs, because calculators, computers are very good at taking derivatives and solving algebraic equations and stuff like this. But there's an aspect to these things of turning a real world situation into kind of a mathematical model that we still need, humans for. And so that's why I really like this type of section. Anyway, let's get to it. So yeah, we're going to be showing how maximizing and minimizing functions, in this case you often say optimizing for short, can have very significant real-world uses. First though, I'm going to go through, there's some geometric formulas that I expect that you should have put to memory. So these are them down here. The claim is if there are any problems out there that need anything more than this, then I will fight to make sure that I will give you those geometric formulas. But these ones I expect you to know. So the first one, there's a couple for perimeter. So of a circle, usually you call this circumference. So circumference is pi times the diameter. Diameter is, of course, 2 radiuses. So that's why this one's written circumference is equal to 2 pi r, where r is the radius. Okay. Of a rectangle, perimeter of a rectangle, remember this is just you add up all the sides. So perimeter, just like circumference, is kind of like the outside bit of, in this case, the rectangle. So if you have length here, height here, length time plus height plus length plus height, so this is 2 L's, 2 H's, so that's where you get the perimeter there. Volume of a cylinder or prism. This one's a little bit complicated, but it's going to be the height times the area of whatever the base is. So if you have a circular cylinder, for instance, it's going to be height times the area of a circle. If you have a rectangular cylinder or prism, I guess prism is what you would call it in that case, you would have height times, maybe like area of a rectangle or something like this. So, okay, this is the volume equation that we need to know. And then we have various area equations. So we can have area of a circle, that's going to be pi r squared. R is again the radius. Area of a rectangle, that's going to be length times height. Sometimes you may say length times width or something like this, but okay. And then area of a triangle, that's going to be 1/2 base times height. So again, these 6 equations I expect you to know. And they may not be given to you on quizzes, exams, etc. Anything more than this, I'll give to you. Okay, so here's the example. Ryan is building a raised rectangular planter box for his vegetable garden. He purchased 32 feet of wood. What length and width will maximize the area of the planter box? So, okay, I'm going to go through and highlight what I think are some important things, So first of all, we know that the planter box is rectangular, So this is telling me a shape. And we are very interested in, we want to maximize area. So I want to maximize area of a rectangle, and of course this is going to have something to do with length and width. He purchased 32 feet of wood, so we're going to need to use that in some regard, because this is telling me kind of the maximum amount of wood that I'm allowed to use for this planter box. So, okay, again, I want to maximize area of the planter box. So let me go ahead and maybe, first of all, I'm going to draw a little bit of a sketch. So, in fact, I'm going to need, I think, more room. So I'm going to draw a line down the middle. And so to the left here, I'm going to draw a little sketch. So again, we have a rectangular planter box. So I'm going to draw a rectangle. We have length and height all around here like so. And we know that we want to maximize area. So area. Area of a rectangle is length times height, or length times width, or whatever you want to say. So area, length times width, length times height. Okay, so I want to maximize this. Well, I learned in 5.1, how to maximize things. I would take a derivative, find critical points, and then classify those critical points and hopefully find a maximum. But my problem here is that I have 2 variables, I'm really good at taking derivatives of things with 1 variable, like x or like t or something like this, but this one has 2 variables, length can be anything it wants to be, height can be anything it wants to be. So I need to try to restrict this down to just have 1 variable. And so I've used pretty much all of this information up here, except for the fact that I purchased 32 feet of wood. So I'm going to use this to hopefully just get down to 1 variable. So 32 feet of wood, that's telling me, at most, how much can my perimeter be? So I'm going to say if I want to maximize area, I'm going to use all of the wood that I have available. So my perimeter should be 32 feet of And so my perimeter in this case, right, is going to be 2 L's plus 2 H's. And if I add all that together, I should get 32 feet of wood. Okay, so now I'm going to go ahead and rearrange this and solve. I'm going to solve for L in this case. So maybe one thing I noticed that I can divide by 2 on all sides. So if I divide by 2, I'm going to get 16 over here. And I'm going to subtract H from both sides. So I'm going to have 16 minus H is equal to L. Now that I've solved for L, I'm going to go ahead and take that and plug it into my equation up here, giving me a formula for area that just has one variable. So it's going to be area is equal to, instead of L, I'm going to write 16 minus H, and then times another H. Getting ready to take a derivative here, I'm going to go ahead and rewrite this as 16H minus H squared. So now this is an area formula, but it only has one variable. And so now I'm ready to maximize, right? If I have an equation, we now know how to maximize or minimize from our knowledge in 5.1. So I'm going to try to find critical points. So I'm going to take a derivative. I'm going to do A prime over here. And so the derivative of 16H is going to be 16. The derivative of H squared is going to be 2H. And if I want a critical point, I want to know when is this equal to 0. And so I have 2H is equal to 16. And so I have H is equal to 8. So H is equal to 8 is a critical point. Now the problem here, right, I would like to maximize the area. What if this actually minimized the area? Or what if it was a critical point that wasn't important at all? So it's very important. Every single one of these problems that you do, you need to actually justify that you found the thing that you want to find, right? In this case, a maximum. I want to justify that 8 is a maximum. So therefore, I'm going to use the full method that we learned in 5.1. I'm going to draw a number line here, and I'm going to plot information about the derivative of area around 8. So I'm going to go a little bit less than 8. I'm going to go to 7. And I'm going to go a little bit bigger than 8. I'm going to go to 9. And I'm going to choose these test points, right? And I'm going to plug them in. And I'm going to hopefully see that this is a maximum. So, okay, remember I'm plugging these things into my derivative back here. If I plugged in 7, I would have 16 minus, 7 times 2 is 14. So 16 minus 14 is 2. That's a positive number. So far, so good. 9. So let's see, 2 times 9 would be 18. 16 minus 18, that's going to be negative 2. That's a negative. And so therefore, my function a is going to be increasing, right, positive derivative, and then decreasing, right, a negative derivative. So increasing, then decreasing, you can see that this is making a maximum shape. So therefore, h equals 8 is actually a maximum. So h equals 8 is a maximum. I want to be very clear with you guys. If you do not show this work, if you do not justify that this thing is actually a maximum, you may not receive full credit. In fact, I won't give you full credit. So this is an important part. You need to actually show that this is a maximum. It's not a minimum. It's not an unimportant critical point. It is the maximum. Okay, now we need to go back, right? We wanted to figure out dimensions, length, and width. We found 8 is a maximum. Now I'm going to go back here. I have, well, it kind of looks a little bit messy, but right here I have a way to say, you know, if you have an H value, you can get out an L value. So let's go ahead and do that. So 16 minus H, so 8, equals 8. That's going to be our L value, is length. So again, the question that asks, what length and width will maximize a planter box? The answer is you should have, I guess, width of 8 and height of 8, and this will maximize the area of the planter box. Okay, so that's the final answer. Nothing more to do for this problem, but I would like to take what we did in this problem and try to bottle it, right? I would like to come up with a technique that we can apply to other types of problems, right? Because this is a little bit confusing, so I want to give us, you know, like a guide to do these problems. So here it is, optimization technique. The first step that we want to do is we really want to read and try to understand the problem. Understand the problem. So while doing this, right, of course, read through it in its entirety and also determine what is given and what is unknown, right? So in the last case, we had that we purchased, for instance, 32 feet of wood. We knew that it was a rectangular planter box, and we wanted to know what were the dimensions that maximized area. The next thing a good idea often is anyway, let's live computer, draw a diagram. Draw a diagram. This won't be useful in all problems, but a lot of problems out there, it really benefits, right? This is just our little picture of the rectangle up there to kind of visualize things. Okay, step 3, introduce notation. Introduce notation. So, right, we're going to assign symbols. That was like our L's and our H's and stuff like that. And also A for area, right? Anything that needs to be maximized or minimized, right? Assign some symbols to that. And we want to select symbols of other quantities and label the diagram when appropriate, right? So in this case, for instance, we decided L was length, H was height. We labeled our diagram. We said A was the area, right? So we're going to come up, but I mean, you could have used like X's and Y's, right? So it's kind of up to you, the notation you select. There's nothing in here, the problem statement, that says, oh, you need to use H's and L's. You could use W's for width, would make a lot of sense. Width and height, or width and length, or X and Y, or anything, right? So you come up with a notation. Number 4, find an equation. Find an equation that relates the quantities with what needs to be optimized. So in this case, that was our area equation, right? We needed to optimize, in this case, maximize area. So the equation that we use in this case was area is equal to length times height, right? The next one, use restricting equations. Restricting equations. To reduce down to one variable. That was the fact that about perimeter, right? Up here we knew that the perimeter was going to be 32, that we had 32 feet of wood, and the wood was actually building the perimeter of this object, right? So it's a lot of interpretation. And then finally, use techniques taught in 5.1, the previous section, to find a maximum or a minimum. That's going to be find some critical points, right? And then classify them using our theorem about, right, we check to the left of the critical point, to the right of the critical point, we figure out what are the sign values of the derivative there, and then we classify. Okay, so this is, in a nutshell, the technique that we're going to apply to our optimization problems. So I'm going to try this. One more problem here in this section. This one's a difficult problem, but I wanted to show you kind of these things can get up there. So it's going to take a little bit, but that's okay. I'm happy that we're doing this in a video. That way you can rewatch it, you can pause it, you can rewind, anything like that. So please take a little bit of time with this one. This is where we're hoping to get to for these types of things. So okay, I have a soup company, Super Soup. Makes canned discount soup that is far from super. What is the minimum cost in creating a cylindrical can that can hold 300 cubic centimeters, right? That's about 10 fluid ounces. And of course we're using steel, and our steel costs 1 cent per square centimeter, right? Per area. Okay, so let's take a look here. Let's see, we want a canned discount soup, we want minimum cost. So we want to minimize a cost function. We have a cylindrical can, and we know something about its volume here, right? The volume is supposed to be 300 cubic centimeters, 10 fluid ounces. And we know that for each kind of area, it's going to cost us 1 cent, right? For each square centimeter, it costs us 1 cent. Okay, so the first thing I'm going to do, right, we've already read the problem, we've tried to understand it and stuff like this. Let's try to draw a diagram here. So we know it's a cylindrical can. So here's our nice cylindrical can, right? And let's see, I actually may want to rip this thing apart a little bit, right? Because I need to build it out of steel. And of course it's not a solid can or anything like this. It's kind of the outside of the can that needs to be built. So I'm going to decompose this can. I'm going to break it apart. Basically if we had scissors or something and we're ripping this thing apart. A can has a top, which is a circle, a bottom, which is a circle, right? So the top part and the bottom part. Let me go ahead here, green, green. So the top and the bottom, which are both circles, and then it has that part in the middle, right? And actually, I'm not gonna. That green's gonna kind of drive me crazy. I can't do that. I'm sorry. Okay, top and bottom, and then in the middle part, the claim is this is going to be a rectangle. That if you were to break apart a can, or in fact at this part you could basically just use a toilet paper roll or something like this. If you were to cut it and then roll it out, right, it would look like a rectangle. This is important because I know area equations for circles and rectangles, right? So for instance, for the circle on top, this is going to be pi times whatever the radius is squared. Likewise in the bottom, pi times the same radius squared. It really depends on what the height of the can is here. So I'm going to use h for height. That's going to be the height of this rectangle. And then notice that if you were to take the rim of the can right here, well, that would be the circumference of the top circle, right? And it would also map to the top of this rectangular piece right here. So whatever the circumference of that circle is, happens to be the length of our rectangle. So circumference is equal to 2 pi r. So that's the length right there. It's going to be 2 pi r, right? Because we kind of want as few variables as possible. We already probably have too much. So that's how we can decompose this can. And why we wanted to look at these area pieces is right because it costs 1 cent for each amount of area, each square centimeter. So let's go ahead and build our cost function, right? So that kind of the next part, we've introduced notation already. If I go down the list again, right, we've understood the problem, we've drawn a diagram, we've introduced some notation, right? We have R's and H's and stuff like that. And now we need to introduce notation for something that needs to be optimized, right? So number 4, find an equation that relates the quantities with what needs to be optimized. So I need to minimize cost. So optimize cost, and I would like to find a minimum. So cost, I'm going to go ahead and call this C. Makes a lot of sense. So our cost function, well, it's going to cost 1 cent times the amount of area, right? So it's 1 cent per unit of area, so in this case, square centimeters. So 1 cent times the amount of area. So it's 1 times something. It's kind of not very exciting, but if it was 2 cents, right, you would do 2 times the amount of area. If it was 3 cents, you would do 3 times the amount of area. So it's telling us our units are going to be in cents in this case. So I want to know how much area is there altogether. Well, if you were to take the area of just the top, right, that would be pi r squared. If you were to take the area of just the bottom, that would be another pi r squared. And if you were to take the area of the siding of the can, well, this is a rectangle. It's supposed to be length times height. So the length in this case is 2 pi r times the height. So 2 pi r h. Okay, so let's simplify this down. This is going to be, right, pi r squared, so that's going to be 2 pi r squared. Of course, 1 times anything is just itself, plus 2 pi r h. And so as before, you can see that we have 2 variables. We have an r and we have an h, right? And we would like to reduce this down to just 1 variable, right? So 5, we would like to use restricting equations to reduce down to 1 variable. And so there's something that we haven't used. We need to use this fact that the can should hold 300 cubic centimeters, right? So this is telling you something about volume. So volume of a cylinder can, right, according to way up here, this one again right here, is going to be height times the area of the base. So in this case, the height of the can, well, we've denoted that as h. So again, volume, we want 300 to be equal to volume. Volume is supposed to be height, which we've called h, that's our notation we introduced, times the area of the base. Well, it's a circle, so it has area pi r squared. So there's our equation for height. I'm sorry, for the area of the base. Blech. So let me go ahead and solve this for height. That's where I was trying to go. So if I'm going to solve this for height, I want to divide by pi r squared on both sides. So I'm going to have 300 divided by pi r squared, that's equal to height, right? Because again, my goal is to use restricting equations, number 5, to reduce our cost equation down to just 1 variable. So, okay, now that I know what height is, I'm going to go ahead and write the cost function as 2 pi r squared plus 2 pi r, and everywhere I see an h, I'm going to plug in this thing. So that's going to be 300 divided by pi r squared. So we can see there's a little bit of cancellation that happens, right? There's a pi in the, oops, I wanted red or pink. I wanted pi in the top, pi in the bottom. There's an r down here. In fact, there's 2, and there's an r up here. So this is going to simplify down. I guess I need to move into my next column here. That cost is equal to 2 pi r squared plus, let's see, 2 times 300, that's going to be 600, divided by r. And remember, in order to start getting ready to take the derivative of this thing, right, I'm going to go ahead and write this as 2 pi r squared plus 600 r to the negative first, right? When you divide by something, it's the same thing as multiplying by it to the negative first, right? Okay, so we are now done with step 5. We've used restricting equations. We have it just in one variable. Now I'd like to use my techniques taught in 5.1 to find a maximum or a minimum, in this case, a minimum of cost. So my first step is going to be to find critical points. So critical points are when the derivative is equal to 0. Let's calculate out the derivative. And by the way, let me note, again, all of this part up until this point, this has been the human part. This has been the setup, right? At this point, I guess, this is where computers and calculators do a very good job, right? But like I said at the beginning of this, there's so much setup to this thing. This is really the important part, is the setup. And often where a lot of points lie in these types of questions is in the setup, because after that, I mean, this is something previously taught in 5.1. This is something that calculators and computers can do very well. But okay, let's go ahead here, and I would like to calculate out the derivative of cost. So let's go ahead here. The derivative, well, 2 pi is a constant. It's along for the ride. And when you take the derivative of r squared, that 2 is going to come down. So I'm going to have 4 pi, and then r to the first power, technically. Okay, when you take the derivative of 600, r to the negative first, again, the 600 is kind of along for the ride. So this is going to be the negative 1 comes down. And then I get r raised to the negative second power, according to the power rule. Okay, another way to write this, because we're going to need to solve here. Remember, I'm trying to find critical points, so this is where the derivative is equal to 0. I'm going to rewrite this 4 pi r minus 600 over r squared. Right? So I'm going to write this, instead of having this negative exponent, you can push it down into the denominator, and then it gets a positive exponent. Okay, now let's go ahead and rearrange this and try to solve for r. So we're going to have 600 over r squared is equal to 4 pi r. We're going to have, let's see if I can do 2 steps in one. I'm going to multiply by r squared on both sides. So I'm going to have r cubed over here. And I'm going to divide by 4 pi on both sides. So this is going to be 600 divided by 4 pi. So now I've solved for r cubed. At this point, it's nice to have a decimal approximation for this darn thing. So I'm going to go ahead and pull out my calculator here. And I want 600 divided by, and make sure to use your parentheses here, we need to divide by all of 4 times pi. Let's see, I used to know where this is. Here it is, second in this little exponent thing. Okay, enter 47.75. 47.75 we'll say. So this is around 47.75. And then I want to take the cube root on both sides. So if I take the cube root of that number, so let's see, I'm going to go into math. There's a place where you can see this little x sign down here, but actually there's a cube root sign. Perfect. So I'm going to do math, and then 4, the cube root of our previous answer. So I'm going to do second and the minus sign down here to do our previous answer. So if I take the cube root of that, 3.627 blah blah blah, I'm going to use 3.63. So 3.63, and right, we can include some units here. That's going to be, of course, centimeters. These are going to be our unit of length. And I think that's a minimum, but I'm not sure, right? So again, just as before, we need to actually show that this is a minimum. So I'm going to go ahead, map information about my derivative of cost around 3.63. And so I'm going to check numbers, for instance, like at 3 and at 4, plug these into my derivative, and see, do I get out positive or negative? So let's go ahead and do that. So I'll pull up my calculator again. And in fact, because I need to plug in two numbers, I'm going to make this a little bit faster. I'm going to do a plot. I'm going to do a plot of the derivative. So I'm going to do 4 times pi times x minus 600 times x raised to the negative 2. And of course you could just do divide by x squared if you'd like. Either way is fine. Oops. Left click. There we are. And now I'm going to go ahead and look at my table. So second graph will give me the table. 0 is of course undefined, right? Doesn't really make sense there. Because then you'd be dividing by 0, right? So you'd have dividing by 0 squared. Doesn't make sense. Okay, so at 3, we can see we have a negative number, so negative. And at 4, we can see we have a positive number, 12 and change, right? Pretty close to 13. So again, if you go from negative, that means our function is decreasing, to a positive, that means our function is increasing, we form a little minimum thing. So this is going to be, so r is a minimum, so 3.63 is a minimum. There we go. And we need to go back and make sure that we've answered the question, right? So what is the minimum cost? Well, the answer isn't 3.63, right? That's a radius value. So I need to get a cost value. So I'm going to go ahead and plug this in up here for my cost function and get what is the cost at 3.63. So again, pull out my calculator. In this case, I'm going to go ahead back to the beginning here. And this is going to be 2 times pi times radius squared. So in this case, 3.63. 3.63 squared plus 600. Oops, there we go. 600 divided by 3.63. Enter 248.08. 248.08. So cost is equal to 248.08. Remember, cost is in cents, so this is cents. So if you'd like, you can also write this as $2.48 will be the minimum cost of a cylindrical can. And that's pretty expensive when you think about it, right? That means I'm probably paying too much for steel, because this hasn't even taken into consideration, you know, my cruddy soup and all that sort of stuff, and, you know, wages and blah, blah, blah. And I see cans of soup at the grocery store for under $2 regularly, so I must be paying too much for steel. Anyway, that is it. That's our final example. You can see this one is more complicated, but if we follow the same optimization technique, we can still get a good result. All right, that's it for me. I'll see you guys next time in 5.3.